So last chapter we saw the power of compounding interest, and we've also, learned from experience that the more compounding periods we have, the faster our money grows if everything else is equal. This question kind of asks us to consider two different interest rates. One's at 2% interest, compounded quarterly. So here's the thing, it's only paying out 2% interest annually, right? But what happens is 4 times a year, they open up the ledger, they look at the balance, they add 1/4 of that percent. In other words, they add 0.5% of the money into the account at that quarter when they're compounding it. So now that account has a slightly higher value, and when you come into the second quarter, same thing, they're going to now apply the 1.5% again. But the thing that's different is now, because we've already earned some money on the previous quarter, we're now earning interest on that previous interest payout. So it grows a little faster. So the question is if you have compound interest that's compounded quarterly versus interest that's compounded monthly, is that monthly compounding enough to make a difference between the 2% interest versus the 1.5% interest? So let's write two different equations that represent the situation here, and then we'll try and track those. Notice they don't give us any dollar values at all. They just ask us, hey, if you're doing it for 5 years or 25 years, which account is better? And maybe we can look at it and extend it out to 50 years or 100 years and see if at some point the 1.5% interest will overtake it, but maybe not. So let's look at the 2% interest first. So if it's a 2% interest, and we're compounding that quarterly, what I'm going to do is take that interest rate as expressed as a decimal, 0.02, and I'm going to divide it into 4 compounding periods for the year. So that's going to, and then that ends up being 0.005. So that's our interest rate for each of our compounding periods. So if I look at this now, this is an exponential equation. Y would be the balance at the end. A is the amount that's put in deposit initially, and we don't know what that A is, so I'm leaving it as a variable. However, I do know my multiplier. In this case, let's see, the multiplier, it's increasing, right? So my multiplier would be times 1.005. So if you look at it, I'm adding the 1 here because this is a percent increase. Obviously, we're adding money to the account. So this 1 is what we add there, right? So that's like what A is plus 5 plus actually plus 0.5% added to that A. And then instead of raising it just to the variable x, what I'm going to do is raise it to 4x. And the reason why 4x is, if I plug 1 in there, that represents 1 year, but it's 4 compounding periods. So this expression right here, or this equation, this exponential equation, y equals a times 1.0005 to the 4x power, represents the value of this account for any year, right? So for any number of years. So if I put in 1 year, 2 years, 3 years. So let's consider the other equation, right? The other equation, the other situation is 1.5%. So not the 2%, but 1.5%. That equation looks like this. We're going to take the 1.5% expressed as a decimal, so 0.015, and instead of dividing by 4, I'm dividing by 12 because this is compounded monthly. So I'm breaking the interest down into 1/12 of a year, and when I do that, we get the very, very small multiplier. Well, that's not the multiplier, it's the percent increase of 0.00125. And the multiplier then that would correspond to that would just add 1 to it. So our equation looks like y equals a times 1.00125. And instead of raising that to the x power, we're going to raise it to the 12x power. So now when I put in a single x, that gives me my 12% or my 1.5%. But it allows it to happen with these 12 compounding periods in the 1 calendar year. So to help visualize this, I've gone ahead and plugged both of these equations into GeoGebra. The first one is let's see, this is, what color did I use? Oh, I didn't color code them. I did, but I don't remember which color is which. Let me hit view and look at my algebra view. Okay, so the one in red is the first situation. So this is going to be red in GeoGebra, and this one is going to be blue in GeoGebra. And when we look at these, let's bring this up here. It's really difficult because there's not a lot happening at this point. So if I deposit $10 in the account and wait a certain number of years, because that's what X is, it's the number of years, you can see there's really not a visual difference at all there. Now I believe if I deposit more, it becomes easier to see. I don't think it changes the outcome, but it does become easier to see. You see this? So you can see red is clearly the one that's on top if you deposit more money. Now, even with just an initial $10 deposit, if I take and I stretch the X scale so that we're looking at fewer dollars, let me just take this and stretch it up. At a certain point, you can see that red is still on top. So the one that is paying the remember the 1.005 for the multiplier is the one that's paying 2% compounded quarterly. You can see that's producing a better outcome with a $10 initial deposit and in 5 years. And in fact, if I take this, let's bring this out. Let me bring this back down to. If I take this and I bring it in so that I can see 25 years of what happens, you can see in 25 years it's still doing better. And in fact, if you accidentally forgot about this account and your great grandchildren found it 100 years in the future, well, let's see, 100 years in the future, that would be really interesting to see how much money that's actually worth. Actually, let me figure that. If I want to look at that, I can graph the line x equals 100. Sorry about this. X equals 100, and of course, it's not going to see that as an x. X equals 100. No. No. Let me use the actual keyboard. So GeoGebra has this it has this on-screen keyboard. So I would just want to look at the line x is equal to 100. So this is 100 years of this account being in effect, and I need to enter that. Darn, I lost my keyboard. I need to press enter. There we go. So what I wanted was this vertical line. So this black line represents 100 years of deposit, and the first thing I noticed is that the first account is only it's actually not paying out very much at all. The first one is only $40. That's practically nothing. In fact, I could throw a point on this line, and if I move this point in here, you can see it's not much cash. So this is better. I've fixed this point so that it stays on the X line, and you can see after 100 years the account is only worth $43. So not much happening there. And the other account, after $100, it's only worth about $75 or so. Now I could take this and say, yeah, well, that's because you only started with a $10 deposit. What if I ramped this up and made it a $100 initial deposit? So if we start with $100, you can see I'm having to climb pretty far up here, so it still isn't that much. It looks like the red line's somewhere around $700 or something. So the money's not really growing fast, and I guess that's not the point. The point is in this situation, 2% beats 1.5%, even if you're going from compounding quarterly to compounding monthly. So in both cases, if it's either 5 years or 25 years, the one that was at 2%, which is this equation, is the winner. So this is the winner.